Okay, so thank you very much, Marta and Renato, for the invitation. I'm really glad to give this talk here. And so I prepared a bit of an ambitious plan for a talk of half an hour, but the my main goal is to give a global picture of this, of a set of works I did in collaboration with Leonor. And I will skip quite a number of details, but I will be happy to answer questions in case I'm skipping too much. Okay, so the plan of the talk is the following. I will first introduce polygon and hyperpolygon spaces that are one character of the talk, and then I will speak of quasi-parabolic and parabolic Higgs bundles on the other side, and show how these moduli spaces relate to each other. And then hopefully I will get to talk about involution that are actually the motivation of the most recent developments of these works with Leonor. So the moduli space of polygons, a first way to describe it is the following. Consider n non-negative real numbers, alpha 1 through alpha n, and consider S2 alpha I, the two-sphere of radius alpha I, equipped with this volume form. So the product of such spheres is naturally a symplectic manifold, on which the group SO3 of rotation acts in an Hamiltonian fashion. With moment map mu that takes values in R3, we can think of it. Of course, it's all of the Lie algebra of the group. And this moment map is simply given by the following rule. If we take n vectors v1 through vn, then their image through mu is their sum as vectors in R3. So the moduli space of polygons is a symplectic reduction of this with respect to this construction. So the symplectic reduction of the product of these two spheres by the action of SO3 considered at the zero level set. So a first comment, of course, we call it polygon space because an element v1 through vn belongs to the level set, to the zero level set of the moment map, if and only if, when we think of it as n vectors in R3, we sum them and their sum is zero. So we come with the last one, we come back to the starting point. We have this closing condition. So this symplectic reduction is the smooth scalar manifold whenever it is a manifold, which is whenever this scalar quantity epsilon I of alpha is never zero for any choices that you may make of an index subset I in 1 through n. Okay, so it's the sum of the lengths alpha I for I in I minus the remaining ones. This quantity should never be zero. In this case, we call alpha generic, and the moduli space is a manifold. Another way to describe the polygon spaces is as quiver varieties. It's actually a very similar description. So a quiver is a collection of vertices and arrows between the vertices. And in this talk, I will focus on star-shaped quivers, which are as follows. So there is a central vertex that I will denote by 0, and then n outer vertices and arrows pointing from the outer vertices to the vertex 0. So Nakajima recipe to construct the Keller variety associated to a quiver is the following. You choose what's called the dimensional vector, which gives you vector spaces associated to each of the vertices. So we chose C2 for the vertex 0 and C for all of the outer vertices. And then the representation of the quiver, given this choice, is homomorphisms between the vector spaces whenever there is an arrow connecting the two. So for each of the green arrows, we have a copy of homomorphisms from C to C2. And as we have n arrows, this space is nothing but C2n, where we think coordinates Q1 through Qn, where each of the Qi is in fact a map from C to C2. Okay, this will be important later. And then the Nakajima recipe tells us that our second ingredient is the group K, which is the group of automorphism of the vector spaces we chose at the beginning. And the group K acts on C2n by conjugation, as in here. And one can compute that this is the moment map. Okay. And the point is that the quotient for the action of K on C2n at the 0 alpha level set is precisely the moduli space of polygons that I have introduced before. Actually, the identification with the previous description is pretty easy to give. If we consider any identification of SU2, of the Lie algebra of SU2 star with R3, then we call VI the vector that corresponds to the traceless matrix QI star traceless part. The star is transpose conjugate. Okay, so with this condition, this first moment map condition here translate to the closing conditions for the polygon, and the second condition translates to the vectors, prescribes the length of the vectors VI. Okay, so far so good. Now we can move to the hyper word. So I here introduced the alpha hyperpolygon space in our papers, or if you heard me talk of this before, this alpha wasn't there, but I want to stress it because in a moment I will talk of null hyperpolygon spaces. So this alpha appears now here. And what do we do now? Essentially, we follow Nakajima recipe to construct the hyperkähler quiver variety associated to the quiver. So the choice of the vector spaces didn't change. We doubled the arrows. So for every green arrow, we now have orange going back. And this translates in the representation of the quiver in this n copies of homomorphism from C2 to C, one for each of the orange arrows. So this the representation of the quiver now is the cotangent bundle to C2n with coordinate QI and PI. And this cotangent to C2n is a natural, of course, hyperkähler structure on which the group K acts by conjugation, as in here, in what's called a hyper-Hamiltonian way. So this just means that it is Hamiltonian with respect to each of the Kähler structures, to each of the three Kähler structures. Okay, so I wrote here the moment maps. If you are maybe not so familiar with hyperkähler reduction, it won't mean much to you, but I wrote them for completeness. And just to comment in a moment. So what we do is we consider the hyperkähler reduction for the action of K on the cotangent bundle of C2n at the level 0 alpha 0 0. So 0 alpha for the real moment map and 0 0 for the complex moment map. Okay. In particular, this relation and this will come. I will comment on them later as well. So in analogy to the polygon spaces, this is what's called a hyperpolygon space. It is a manifold, a smooth hyperkähler manifold, exactly when the scalar quantity epsilon I of alpha that I have defined before does not vanish for any choice of I. So when alpha is generic, the definition stays valid. And then M alpha, of course, sits inside the hyperpolygon space as the collection of hyperpolygons where the p coordinate is 0. Okay. Now, the somewhat more new part of the talk is the construction of the null hyperpolygon space. So what we want to consider is the case when alpha is 0. But we can't do it right away. We need to restrict to this level, to this set P0n, where essentially it's the intersection of the 0, 0 level set for the real moment map and 0 for the complex moment map, where we take away all the points where, so essentially we don't allow P and Q to be simultaneously 0 for any I. Okay, because this would give a singularity when we do the quotient. So with this restriction, K acts freely on this ad hoc restriction, P0n, and the quotient by the action by conjugation of the group K is exactly the same action as before, is the smooth hyperkähler manifold, again of dimension for n-3. Okay, so in a way, it is a limit situation when we allow the length to be 0. Any question before I move to the bundle word? Okay, so quasi-parabolic and parabolic Higgs bundles. Let's first define the quasi-parabolic situation. So let E be a holomorphic bundle on CP1 of rank 2. I mean, of course, you can construct the theory in bigger generality, but I am restricting to the case I need to consider. And let x1 through xn be n distinguished mark points in CP1. Then the quasi-parabolic structure on E is a full flag in each of the fiber over the mark points. So I like to draw. Here we have a drawing. I have 4 mark points. Here there are the fibers for each of the mark points that are C2s, because rank 2 is 2, and then I have a full flag. Then there is a notion of quasi-parabolic degree and slope that is here. The quasi-parabolic degree is just the degree plus 2, the number of mark points, and the slope is defined accordingly, dividing by the rank. Okay, and in terms of this, sorry, I will need the stability later to talk. Sorry, the quasi-parabolic slope to talk of stability, but first let me introduce the Higgs bundles. So here is the new part before I just resume what I said. A quasi-parabolic Higgs bundle over P1 is a pair E phi, where E is a quasi-parabolic bundle, and phi is an element in H0 of CP1 with value in the sheaf of strongly quasi-parabolic endomorphism of E, twisted by the canonical bundle of P1, twisted by D. Okay, if you're not familiar with Higgs field, you will probably not be more familiar to it by the end of the talk. But I mean, please keep with me, and I will show you another way of thinking of the Higgs field that is maybe more intuitive to a symplectic geometer. So then, as promised, let me first comment. Well, a quasi-parabolic SL2C Higgs bundle over P1 is a rank 2 quasi-parabolic bundle, quasi-parabolic Higgs bundles, where the E is trivial determinant and the Higgs field is traceless. And then there is a notion of stability that I put here in case somebody, I mean, to give some detail, but it's a notion of. Yes.
Can you just come back a little? So what's happening over the critical points with that endomorphism? We are kind of like collapsing over the smaller part of the flag when we call. So you have this full flag over this finite choice of points, yes. Right? And then next page you define.
Yeah.
You have a pair and then phi is a section.
Yes. So essentially, phi is a 2x2 matrix of meromorphic 1 forms that are endomorphism valued, strongly quasi-parabolic endomorphism valued. So in the marked points that are not singular, just marked points, the Higgs field is either upper or lower triangular because it has to preserve the flag. The endomorphism has to preserve the flag.
It's kind of like not collapsing the flag. The X1 it needs to go to send to the kernel, right? The C needs to go.
Yeah, so the xi1 in my notation is kind of the biggest one. and it goes to the smaller one.
Yeah, okay.
Yeah.
That was my question. Okay, thank you.
Yeah, and this is exactly why in those points it will be of this form, because the residue effect of the Higgs field, but anyway. Okay. Good. So, okay, the notion of stability, maybe I'll skip. It's some notion that is given in analogy to what is known in the literature. And then we construct this moduli space, H0n, of stable quasi-parabolic SL2C Higgs bundles. Okay. So in the next couple of slides, I want to take the quasi, and I just want to talk of parabolic Higgs bundles. Again, I will be kind of fast. The only change is that we choose weights for each of the flags. Okay, so the flags, they come with weights beta1 and beta2 associated to the two-dimensional or one-dimensional space in the flag. And this changes the notion of parabolic degree accordingly, and of parabolic slope. And this is, I mean, for the quasi-parabolic case, we introduced it, but in this case of the parabolic Higgs, this is very well known in the literature by, I think the first who introduced it was Simpson. Should have written it somewhere. And E is stable if the slope of a bundle is strictly bigger than the slope of L for any parabolic subbundle. And with this notion of stability, we can consider the moduli space of parabolic bundles over P1 that are rank 2 and degree 0. Okay. And now, in analogy to what we saw before, we introduce a Higgs field on parabolic bundles. So an Higgs field on a parabolic bundle is an element in the H0 of P1 with values in the sheaf of strongly parabolic endomorphisms twisted by K and D. Okay, it's before. And if E, such a pair if E is what we call the parabolic Higgs bundles. The notion of stability extends in a natural way. And then what we called HB is the moduli space of beta stable rank 2 holomorphically trivial parabolic Higgs bundles over P1 with fixed determinants and traceless Higgs field. Okay, so lots of definitions to begin with, but now they all come together. So in a work of a while ago, 2013, Leonore and I proved that these two spaces are diffeomorphic. So the alpha hyperpolygon space and the moduli space of parabolic Higgs bundles are isomorphic, and in fact they are symplectomorphic whenever the length of the hyperpolygon is given by the difference of the parabolic weights. Okay, and the proof is very constructive. It has it permitted us to do the computation very explicitly. So if we start with the hyperpolygon PQ, I need to give you a parabolic Higgs bundles. So as a bundle, you know, the bundle has to be holomorphically trivial. So it's CP1 times C2. Then I need to give you a parabolic structure, which means flags, full flags in each of the mark points. And here, so in each of the mark points, the full flag, it just means to give a way of putting a copy of C inside C2. And this is done by the coordinate QI. The weights were prescribed at the beginning. And now we need to construct an Higgs field from the hyperpolygon. So in here, we remember one of the moment map condition, which was this one, that the sum of the QI, PI traceless part had to be 0. Okay, so we set these matrices here as the residues at the mark points for our Higgs field. And then by a version of the Residues Theorem, we showed that there exists, and it's unique, an Higgs field that satisfies this condition that has prescribed residues. So this construction, in fact, we realized recently, extends, I mean, once you make the right definitions and construction, extends to the case of null hyperpolygons and moduli space of quasi-parabolic Higgs bundles. The construction, the proof is uses the same idea. Okay. So we recently found this analogy, and now I would like to use my remaining 10 minutes or so to speak of involution, which are in fact, you will see soon, one of the reasons why we thought of this kind of limiting situation where we left the length to be 0. So what we proved back in 2013 was that if we consider the involution either on the hyperpolygons, it takes PQ to minus PQ, or in the language of parabolic Higgs bundles, just changes signs to the Higgs field. Then this is obviously an involution on both spaces, and we studied the fixed point of this involution that are related, that are of much interest because they are related to brains and to to trying to understand the Langland duals manifold. I will get back to that in a moment. So the fixed points of this involution are simple to describe. We have the moduli space of parabolic bundles where the Higgs field is identically 0, which correspond to the moduli space of polygons where the P is 0. And then there are some other components that can be described explicitly, as in here. Essentially, what happens is that the bundle E splits into the sum of two line bundles, L0 and L1. And what happens is that the parabolic structure at this bundle E is prescribed by the splitting. So for each of the mark points I, where I belong to S, we have the same flag. And for each of the point I, where I belongs to S complement, we also have the same flag in green and red in this slide. Okay, so this is kind of cute, but yet we weren't. We would have liked some more. I don't know. Some more polygon-like description of this fixed point set. And this came by noticing. So this is a bit of a hand-waving slide. But what we did so far is we considered a group, for example, SU2, and we took a bunch of cojoint orbits of the group and considered the diagonal action of the group on the product of such cojoint orbits, okay, which is Hamiltonian with moment map, this one, taking n vectors to their sum. And then we studied this quotient. This quotient of a product of cojoint orbits by the group G is what we call the polygon space. So generalizing, we may call it G polygon space. So far we have described the case SU2, which gave us the polygon space. It was kind of implicit that SL2C would give us the hyperpolygons, but there is a character that is missing in this picture, which is the other real form of SL2C, right? Which is SL2R. And this is where it comes into play. So if we consider SL2R polygon spaces, what do we need to do? We need to consider the Lie algebra of SL2R, which is R3 with the Minkowski norm, okay, minus, minus, plus. And this Lie algebra, this R3, is divided by the light cone into 3 regions, essentially. So we have the space-like vectors whenever we have a vector that has inner product with itself negative, and they are kind of here. Okay. And then there are the vectors on the light cone that are the vectors that have inner product with themselves 0. And then there are the products that are inside the light cone. So they have inner product with themselves positive. So they are called either future or past vectors. They are time-like vectors. Okay. So according to this description of this Lie algebra, we can recall what are the coadjoint orbits of this Lie algebra, and they are the 2 pseudospheres, past and future, sorry, the 3 in fact. So time-like, future pseudosphere, and past pseudosphere, depending on the sign of t. And then we have the space pseudosphere that is formed by vector of space type. And then there are the 2 parts of the cone, the positive and negative, so past and future light cone, and 0. Okay, so if we play the game considering time-like coadjoint orbits, so future or past pseudosphere, you can play the game. The action of SL2R on this product is surely Hamiltonian with this moment map. Can consider the quotient. It is in fact a smooth manifold. It was studied by Philip Foth. And it is smooth, sorry, when alpha is generic, again. Okay, the very same definition. And what we realized with Biswas, Florentino, Godinho, myself, is that the fixed components, before I had described just this one, the fixed components for the involution that sends, so the involution I was considering is this one in terms of Higgs field, or that one. They are precisely modular spaces of polygons in the Minkowski 3 space, so in the Lie algebra of the other real form, of the real form SL2R. Okay, the construction is again very explicit. I just put it here again. You just need to stare enough to the moment map condition and realize how you need to build this analogy. But I want to move forward because in this null hyperpolygons, sorry, this is the H. In this, there is also natural involution that we can consider in the, no, it was right. This is an involution in the space of null hyperpolygons, okay, that takes PQ and sends it to Q transpose and P transpose. So we studied this fixed point set. Here is a description. And sorry, maybe that was overly fast. You know, there are somewhat some technical name, but it's not, I mean, I think the cool part is that these components correspond to considering the product of light-like coadjoint orbits. So here we have a product of copies of the past light cone and of the future light cone. We consider the diagonal action on the product, which has this moment map, and then we take the quotient at the 0 level set. We need to restrict again, of course, to the regular points. This is what we call the modular space of closed null polygons in R21. And it is exactly, oops, sorry. Yeah. What I want to say is that the involutions, these spaces that are fixed by this involution, are precisely this quotient, so it was missing. Okay, so you may wonder, and I just take 1 minute more, you may wonder, so what about the, there is a missing, there are some missing guys in this picture, the space-like case, essentially. So what happens when you take a product of space-like quadjoint orbits? That is coming soon. In fact, we recovered that situation when we consider the fixed point of this involution. Okay, so this was based on these papers, and thank you for your attention.